We're now looking at three more functions that are commonly used to demonstrate transformations. The cube function is f of x is equal to x cubed. Because this function is a polynomial, we know that its domain is all real numbers. And that means that we can plug any x value in that we want. I'll choose some x values that are pretty close to the origin, and we now want to look at the corresponding y values for each of these inputs. So we evaluate the function at 0, and to do that we open up a hole for the x and plug in the x coordinate 0 to determine who the corresponding y value is. So when x is 0, y is 0. When x is 1, we're going to cube 1. 1 cubed is 1, and that's the corresponding y value there. We'll be plugging -1 in for x, that will then be cubed. Since we're cubing the negative as well, this output is going to be -1. Let's continue by evaluating the function at 2 and evaluating the function at -2. So we have x cubed in both cases. Here we plug in 2, here we plug in -2. 2 cubed is 8, and -2 cubed is -8. So these are the two corresponding outputs for those inputs. Now we're ready to plot all these points in order to help us determine the shape of the graph. So we plot 0, 0, 1, 1, -1, -1, 2, 8. My Cartesian plane isn't quite big enough, but let's just say it's somewhere up here, and -2, -8, which again we'll have to estimate is somewhere down here. The shape of this graph is kind of snake-like. It does need to pass the vertical line test. Notice that the image appears to have a domain that's all real numbers. And let's also mention that the cube function has a range that is from -infinity to +infinity as well. When we use the x cubed graph in our transformations, we'll want to keep track of these three ordered pairs and where they land to ensure that our transformation of this graph is in the right spot. We'll consider these to be our points of interest. Next, let's look at the cubed root function. While it may not be algebraically obvious, the domain of this function is also all real numbers, meaning that we can plug in anything that we want for the x values. Again, let's keep our inputs kind of close to the center, but since we're going to be evaluating the cube root, let's jump out to 8 and -8 so that the cubed root of those domain elements turns out to be an integer. So we'll begin by determining the function evaluated at 0, which is going to be the cubed root of x, and we plug in 0 to get the corresponding output. The function evaluated at 1 is going to be the cubed root of x. Plugging 1 in for the independent variable, the cubed root of 1 is 1. And then let's evaluate the cubed root of -1, and the cubed root of -1 is also -1. So the output when x is equal to 1, the cubed root of 1 is 1. When x is equal to -1, the cubed root of -1 was -1. Now let's evaluate f at 8, which will be the cubed root of x, plugging 8 in. The cubed root of 8 is 2, so 2 is the corresponding output. And finally, the function evaluated at -8 is going to be the cubed root of x with -8 plugged in, and the cubed root of -8 is -2. So now we have several ordered pairs that we can plot in order to get a feel for the shape of this graph. Starting with 0, 0, we also have 1, 1, and -1, -1. Again, our Cartesian plane isn't quite big enough, so we'll have to kind of improvise and show that our 8, 2 ordered pair is somewhere out here. And let's say our -8, -2 is the ordered pair out here. The shape of this graph is similar to x cubed, except for it's a little bit on its side. Again, we do need to be careful because it is a function, it does need to pass the vertical line test, so be careful in this region to make sure that it doesn't double back on itself. When we're using the cube function and performing transformations, we'll want to keep track of where these three ordered pairs land. These are the ones we'll refer to as our points of interest. The third graph that we'll look at in this video is the absolute value function. This function again has a domain that's all real numbers, which means we can plug anything we want in for x. Let's keep our input values close to the origin and evaluate the function at 0, which this time is the absolute value of x, and we're plugging 0 in for that x to get the absolute value of 0, which is 0. The function evaluated at 1 is the absolute value of 1, which is 1, so 1 is the corresponding output. The function evaluated at -1 is going to be the absolute value of -1, which is positive 1. So we get positive 1 as an output when negative 1 is plugged in. The function evaluated at 2 is the absolute value of 2, which is 2. And the function evaluated at negative 2 is the absolute value of negative 2, which is also positive 2. So let's plot these ordered pairs to get a feel for the shape of this graph. We have 0, 0, 1, 1, negative 1, positive 1, 2, 2, and negative 2, positive 2. When we connect the dots, we actually are going to be connecting them with nice straight lines here, and this graph has the shape of a V. Again, we mentioned that the domain of this absolute value function is all real numbers. The range of this function is starting at 0 and going to positive infinity. We do include 0 in the range.